Welcome to this screencast on objects and classes. So far we've covered subroutines, control structures, variables, member variables. So now we talked about how you can build a program by figuring out what tasks need to be done. So now we're going to add an additional tool to our problem solving skill set, and it's objects and classes. So previously we talked about subroutines being tasks. You would do something in a subroutine and you can do it again and again. We're now adding the concept of an object which combines both data or member variables and subroutines or behavior. So we can now do things, behavior, on that set of data, and we can actually have two separate objects that represent things that have different data in them but have the same behavior. There's a slightly different point of view of how you do problem solving, how you do the figuring out how to solve the problem. So now instead of just finding out what the tasks are, we figure out what the right objects are to model the problem. So we want to actually think about, if we're talking about playing cards, well, we would have like a deck and a card and maybe a hand and those kinds of things. And then we will create the objects that represent those. So it's a different way of solving the problem, but it's very similar. So objects, as we have here, we have classes describe the objects, and classes are used to create the objects. And this is a class that we've played with before, or you should be familiar with the idea that you have a static string name and a static in age, and that they're associated with the class. So there's only one version of them, and they're associated with the class. And if I want to use it, I say userdata.name, and so I get access to it there. But with this class, I have a static int player count, which is associated with the class, but I have a non-static name and a non-static age. So if we draw the picture, it looks very similar, where we have a class player data with a static member variable player count and a constructor for constructing these instances of player data. So now let's construct one. And so we create an instance of player data. It has its own name and its own age, independent of the class and independent of any other instance, but it also can refer back to the player count in the class, so it has access to player count. Let's create another one. And so we have two instances of player data. They're separate, they're not the same, they're different, they both have names, they both have ages, but they're not related, and they both can access the player count. So that's slightly different than our static version where everything was in the class. So now we can create these instances of objects. But we had to create it by a class as an instance. They all have member variables. If the member variable is static, that's associated with the class, so it's called class variable. If it's non-static, it's associated with each instance. They each get a copy, so they're called instance variables. Same thing applies to methods. If you have static methods, they're associated with the class, so they're class methods. And if you have non-static methods, they're associated with the instances. So each instance gets its own copy of the subroutine or the method. And again, when we're talking about objects, we tend to use the term methods for subroutines and functions. So I'm going to probably switch back and forth when I'm talking about methods on objects. I may not use subroutine, but I've been using subroutine for 8 weeks now, so I might continue using subroutine. So the fundamentals of objects makes things a little bit different. For example, this class student has no static member variables, has no static subroutines or methods, so therefore this class is only there to help you create new instances of student. Each instance has its own instance variables and the methods, like I talked, and classes can be used like types, just like you use an int and a string. So you can declare a variable of type student by just saying student and then the variable name. So we declared a student std. So declaring a variable does not actually create an object. It just creates a variable of type student. The variable does not actually hold the object. They hold a reference, so they have a thing that says this is where the thing I refer to or I point to exists. So they don't actually hold the object, they actually just point to it. So to create a new object, you have to use the new operator, and you say variable equals new and student or type. So once we have created the student, we can now refer to the instance variable in std by saying stt.name, std.test1, test2, test3, and we can use it by encoding by saying system.hello student name, std name, and that will refer to std's name, which could be different than any other student that we've created. So how do we use these objects? I just showed you how you can get the instance variable to call the instance method. You use the variable name, dot, and then the method call. So if I wanted to get the average scores for this excuse me, student, I would call std.getAverage. So you can use it, print out the student's average. There's a way also, because the variable is just holding a reference to the object, if you assign it the special value null, now that variable doesn't refer to any object, it points to nothing. So you can check to see whether or not the student is equal to null. Now, if you assign std to null and then ask std what's your name, so you did std.name, that will lead to a null pointer exception because null doesn't point to anything and there is no name associated with null. So that's one of the often exceptions you'll see when you're using objects and variables of different types. You'll see a lot of null pointer exceptions if you didn't actually call new, because your variable is actually null and you can't access any of the instance variables or instance methods on null. So here's an example of doing the instances. So we create 4 students variables of type student, std1, std, std1, std2, std3. So here's an example on the left hand side of my 4 variables. There are no objects at this point. So here I create a new student and I have std points to that new student. New student's out there in memory someplace on the heap, and std holds the location of where that student is on the heap. So std points to or refers to the new student that we created. If we do std1 equals new student, we create another instance of student different than the one we created before, and std1 now points to this other student. Now if we do std2 equals std1, that does not create any objects. That's just saying point std2 at what std1 points to. So we did not add any new objects. We still only have 2 instances. std1 and std2 just happen to point to the same thing. So, and then if we say std3 equals null, we actually insert the value null into the std3 variable. So now it doesn't point to anything. So now if we say let's set the name of std name equals John Smith, now name in the instance pointed to by std is pointing to an instance of the string John Smith. And so now if we say std1's name is Mary Jones, so std1's name points to Mary Jones, but because std2 points to the same thing, std2's name is also Mary Jones and is pointing at the same string. So you could say std2.name equals std1.name, and it's true because they're actually pointing to the exact same thing. So I was talking about object equality. So variables that point or are references to objects, you can use the equal, equal, and not equal, but that's comparing the value in the variable. So it's just a pointer. So it only compares the references. If you really want to compare the instance variables stored, you actually have to compare the instance variables. So you say, in the first example, if I say std equal equal std1, the answer is false because they don't point to the same thing. But I could say std test1 equals std1 test1, and I test all the things, and they could be equal even though they don't point to the same instance if all their values are equal. So there's some consequences of this idea of references. I can create a final student stu and initialize it to the new student, And since I use the keyword final, I can't change the value of stu. So stu cannot change, so the reference to that new student cannot be changed. But I can say stu.name equals Jane Doe. That doesn't change the value stored in stu. It changes the value that stu points to's name. So that is completely legal. It's legal to change the data in the object, but I can't change the values stored in stu because I've said it's fine. So you can see the code where if I have a function or a method called don't change, it takes an int, I assign that parameter to 42, I then call it with an int value 10, it doesn't actually change the value of x, because what really happens is z is assigned x's value, which would be 10. We then change z to be 42, but x's value didn't change. Whereas on the right hand side, we have a method called change, where we take in the parameter s, which is a student, and then we assign s's name to be Fred. So we create stu and we set the name to be Jane. We call it change on stu. Well, we didn't change s or stu, that didn't change. But stu's name was updated. So once we're done, we will have changed stu's name from Jane to Fred. So there's one level of sort of indirection. We didn't actually change, the parameter is not changed, it's the thing that the parameter points to, its value was changed. So it's a good practice in general to make your member variables private, because you don't want the outside world mucking with your stuff. But if I make them private, they're not visible to the outside world. So how do we grant access to these private member variables to outsiders? So the answer is you provide a public accessor method. So I have my private instance variable title, which is a type string, and then I have a public method get title that returns a string and it returns the title. And by convention, you use those accessor methods or get methods. They use the word get and then the variable name with a capital, so it would be get title with a capital title. Now, if you're doing a Boolean instance variable, you often use is, because that makes more sense. Is safe or is home returns a Boolean versus get home. So because it returns a Boolean, the verb is. Now, if I can get it, I probably may want to be able to change it, have the outside people change it. So how do we have, if the member variable is private, how do we let them change it? We create a public setter method. Again, we use the convention, we say set and variable name. So we say public void, we have no return type, set title, takes a new title of type string, and then we assign the title to new title. So now people in the outside world can call my public method and change my title. So why would we want to do this versus making the variable public? There's two big reasons. One, you don't want people mucking with your stuff, because what if you decide next week to change the type of your member variable to make it more convenient for you? You then have to go tell every programmer who's used your member variable, I changed the type, or they're going to find out the next time they try to run your program, or their program is going to blow up because you changed the type of something that they are referring to publicly. And secondly, getters and setters don't have to just return the value or set the value, they can do additional work. For example, you may want to count how many times someone gets your title, or you want to make sure that the title is always set to a string and not null when it's being passed in. So there's some very good things that you could do above and beyond just giving them access to your member variable. So it's better to make them private and give, if it's correct in your design to allow them access, write an accessor. If they can change it, you can give them a setter. So give them a getter and a setter. Arrays are similar to objects. So I just want to briefly go over the similarity of arrays. And then conceptually, arrays are objects. So right here we created an array of type int, an array of ints, type list. or we declared a variable list of type array of ints, and we declared a variable new list of type array of ints. That doesn't actually create the arrays, right? I mean, that just creates the variables. So now we have to say new int and the size. So that actually does create, that's very similar to the new student. We're creating the actual memory in, allocate the space in memory, but don't actually initialize any of the values in there. And then if we assign the second item to be 17, and then we point new list to list, new list's item at position 1 or index 1 is 17, but if we change it, we've also changed list's item at index 1 also, because they point to the same array. So, and we can create arrays of objects. Again, it's just the same thing. We create, this declares an array of students called class list. It doesn't allocate any space. It doesn't initialize any students. It just declares a variable. So, because we have to create these instances, we need a way of building them or telling Java how to build the instance, right? Because if you just declare the variable, that doesn't actually create the actual instance of it. So we must construct it. So we use the new operator, just like I talked before. So you declare a student stu, and then you have to say new student, and when you see the student with open close parens, that's a method, or actually the constructor, that's used to create and initialize the new student. These constructors are a special type of subroutine. Java provides default constructor for you that takes no parameters. To write the subroutine, they don't have a return type, so it's got the name of the class. And oh, by the way, the constructors cannot be static. They are not instance methods either, because they're more associated with the class, telling or defining how to create these instances. They're not part of the instance, they're part of the class, even though they're not static. And they can't be static. So example here, we've got the class pair of dice. It has two private ints, die1, die2. Our constructor is public. It's got the name of the class. Notice no return type, takes no parameters, and it initializes die1 to a random number between 1 and 6, and die2 from a random number between 1 and 6. And so now when we create a new instance, die1 will have a random value, and die2 will have a random value. Constructors, if you, and I sort of told a fib a couple slides before, Java provides a default constructor as long as you don't provide a constructor that takes parameters. If you provide a constructor that takes parameters, you must provide the default constructor. So in this example, since we added the public pair of dice that takes two values, then we must create the default constructor that takes no values. So in this case, we can now have the default value of, when we run the default constructor, we call the method roll, which assigns random values to die1 and die2, or we can take the other constructor where we supply two values and assign those values to die1 and 2. So remember, if you provide a constructor that has parameters, you also need, Java will not provide you the default constructor for free. So what are the steps in construction? The first step is the JVM finds enough space for the object out on the heap. It then initializes any instance variables. It then sets the actual parameters for the constructor, if any. So in the pair of dice, int val1 and int val2, it actually will go get the value, it sets those parameters. It then executes the statement of the constructor, which would assign die1 to val1 and die2 to val2. And then it returns a reference to the object to the variable on the left-hand side of the assignment operator. So, instances, we've talked before, can access static members of the class. So here we have the example of a student where we have a name, an ID, and a private static int, next unique ID. So that's stored in the class. And in the constructor, we can take the name, we assign it to name, we increment the static variable, and then we assign that incremented value to our ID. And therefore, every student will have a unique ID as long as we have a single threaded program. If we have multiple threads, the two threads might go through the constructor at the same time, and you have a race condition, and you may get them both getting the same ID. But don't worry about that. That's later on in several years or several more classes when we talk about threads. So we've created these things. Now, what happens when we get rid of them, or we no longer have any references to them? So we create a new student, John Smith, and we assign it to the variable std. And in the next statement, we say, well, std is now equal to null. Well, that instance of student is still in memory and is on the heap, but you can't refer to it anymore. There's no way to access it. No one points to it. It's out there, and it's just wasting memory. Well, in some languages like C++ or C, you, the programmer, need to allocate the memory by calling new or malloc, and then you actually have to free up the memory when you're no longer done with it. Now that's wonderful, but it's a very tricky thing to do. If you don't free up the memory, you can run out of memory, and it's all wasted on things you can't refer to anymore, or you can accidentally try to free up memory twice, and it may have been reallocated to someone else. So it's a very tricky thing to do, and it's a constant problem, and it's something that can cause lots of problems in your programs. So Java gets around that because Java automatically reclaims the memory for you, and you don't have to worry about it as a Java program. It's a very nice feature of Java that it does its own garbage collection, and the memory of objects that are no longer referred to is considered garbage, and it can be freed up. Thank you very much for your attention.